Robots are everywhere. They're not just confined to factories anymore. They're in our gardens, our homes, and even inside our bodies. With humans and robots collaborating more and more closely, safety becomes an important concern. One innovative approach is to use soft robots. These robots, made from soft materials like rubber, they can, for example, deform around obstacles, making them inherently safe. The versatility of soft robots brings several added benefits. They excel in navigating through unstructured environments, maneuvering into tight spaces, and they can handle irregular objects with relative ease. Yet, a significant drawback of these soft robots lies in their limited lifespan. The soft materials that they are composed of are, for example, susceptible to damage from sharp objects in their environment. As soft robots are often inspired by organisms found in nature, such as octopuses and elephant trunks, it is not surprising that biomimicry also provides a solution here. When natural organisms are damaged or injured, they will eventually recover and heal. Mimicking this ability, soft robots can be constructed from self-healing polymers. This enables damaged robots to be restored simply by reassembling the pieces and heating them up. But how does this self-healing process work? These remarkable polymers rely on the Diels-Alder reaction. The Diels-Alder bonds serve as the crosslinks within the polymer network. And this reaction is thermally reversible, meaning that the crosslinks in the network can be formed and broken by changing the temperature. At room temperature, most of these bonds are formed. Upon heating, the equilibrium shifts, progressively breaking more and more bonds. At a certain temperature, so many Diels-Alder bonds are broken that the material no longer forms a single network and it transitions into a viscous liquid. This critical temperature, known as T-gel, it enables reprocessing of the material. However, for healing to occur, it's essential to maintain the geometry, and it should therefore be done in a solid state below this T-gel. Upon cooling, the equilibrium restores, enabling the bonds to reform also over the interface between the two pieces, and effectively healing the damaged area. To transform these materials into soft robots, they need to be processed. And there are plenty of methods available for manufacturing soft robots, including casting, injection molding, and various 3D printing approaches. Each method comes with its own set of advantages and disadvantages. So, selecting the best one, it depends on a specific application. I focused on exploring how these self-healing materials can be used for fused filament fabrication printing. In this technique, a motor pushes a filament through a hot printing head and out of a nozzle. As the material passes through the printing head, it liquefies. And once deposited, the material must rapidly solidify. Now, traditional thermoplastic polymers achieve this through cooling with a fan. However, for self-healing polymers, cooling it down is ineffective, and it even has the opposite effect. While this is counterintuitive, this phenomenon is logically explained by the nature of the liquid to solid transition. Unlike melting, this transition is based on breaking and reforming of the Diels-Alder crosslinks, which is a chemical reaction. And as these reactions slow down at lower temperatures, cooling down also slows down the solidification process. This shows that printing these self-healing materials needs a bit of a different way of thinking. Now, besides their self-healing capabilities, which are beneficial for printing soft robots like this gripper, there is another significant benefit. Typically, parts fabricated using this technique have anisotropic mechanical properties, which poses a major challenge. As layers are stacked, the part is weaker along the direction of layering and stronger within the layer plane. However, with self-healing materials, the formation of strong Diels-Alder bonds between the layers solves this issue, as the layers effectively heal or fuse together, which is a very important result. Just as we fuse layers together during printing, we can also fuse different self-healing materials. Materials with different mechanical properties can be obtained by adjusting network design parameters like stoichiometry, spacer length, or by incorporating fillers into the network. But why would we do this? Well, the ability to seamlessly integrate multiple materials makes it possible to create more complex robot designs and to enhance their functionality. One of these crucial functionalities that we can introduce is sensors. Given the nearly infinite degrees of freedom of soft robots, it is not only useful to obtain information about their environment, but also about their own shape. And when working with self-healing robots, it is important that their embedded sensors are self-healing as well. To achieve this, the first step is developing conductive self-healing polymers, which was done through the addition of carbon black particles to the self-healing matrix. To create sensors, I extruded this conductive material into thin fibers of roughly 0.5 millimeter in diameter. When these fibers are strained, the resistance changes, and thus, when they are embedded within a soft gripper, monitoring the resistance variations provides information of the bending and shape of the fingers. But also other types of sensors can be created, including capacitive force sensors. By constructing a sandwich structure of two conductive layers separated by a non-conductive layer, a flexible parallel plate capacitor is formed. When compressed, these plates come closer to each other, increasing the capacitance. This principle can be used to measure the force exerted on grasped objects. All these sensors have proven full recovery of sensing behavior even after severe damage several times in a row. With the advancement of sensors and processing methods for self-healing soft robots, my research lays the foundation for further developments in the field of self-healing soft robotics. And these advancements not only prolong the lifespan of soft robots, but they also address sustainability concerns, as typically soft robots are often made from non-recyclable materials. Thus, these self-healing materials are promising to create a more environmentally friendly future for soft robotics.